All right, this fourth and last video for goal 1 of this new unit on differential equations is going to just be the promised solutions to the problems I said, hey, try yourself. There's a little bit of a twist to one of them, so you can see how far you took the answer, but the answer can most likely be taken farther than what you did on the second one. So these are the two problems. I said try it on your own. These are the solutions to them. Now, I skipped a few steps because when I was showing them on the other videos, I tried to be explicit as possible. Basically, on this one, I multiplied the y over, multiplied the dx over at the same time, and then integrated both of them. So I sort of jumped to that step where they're already separated and I'm integrating them. I got their antiderivatives. I put these little lines here because I decided to get the c right away. And then after I got the c was 1/2, I went through and solved it. All right, so the solution to that is actually, there are two functions that work. Y equals the square root of 2x cubed plus 1, and y equals negative the square root of 2x cubed plus 1. All right, so technically the answer to this actually, there's separate pieces that are functions, but the entire thing put together, it would be a relation because there's basically going to be a top half and bottom half to this. But these two functions make up the answer to this. All right. Now, the other one, now they had a dt in it, so they didn't show the t on the other side, but hopefully you were able to separate it anyway. Because even if you have a number, I still need the y's on one side, and even though I don't have a t in the other expression, I still need to move the dt to the other side. So there's basically just a constant on the right side. Now you could have dragged that 4 over with it, but then you would have needed a u substitution for the integration. So what I would do is to make your life as simple as possible, when you're working with this thing, leave the number over on the other side and just move the y over. So I divide the y, multiplied over the dt, and then integrated. Now the 1 over y, remember that's a special integral. The integral of 1 over y, its antiderivative, is natural log of absolute value of y. And the antiderivative of 4, because it's in terms of t, it's being integrated with respect to t, it's 4 dt. Its antiderivative is 4t. I put the plus c on the side with the t because I want to get the y alone, and I can do that. The way you get the y alone is to remember from pre-calc that there's a little e under here, and you do the little tornado thing. It's basically to get rid of this natural log, you have to rewrite as e to this power equals the absolute value y. So that's how I got the next line. Basically, the absolute value of y has to equal e to the 4t plus c. Now, I can get rid of the absolute value bar because it says the absolute value has to equal this e to the 4t plus c. Since this is an exponential function, e to any power can't ever come out negative. So basically, I don't need the absolute value because there's no way that y could be negative. This thing on the right's always positive, so the right side have to always be positive. So basically, I just ditched the absolute value bar. You have to be careful with the absolute value bar and other kinds of functions, but because it's exponential functions are always positive, so we don't need we'll never get the negative version of y. All right, so from here, this is an answer, but later on we're going to see some applications of these differential equations. And one of the popular ones is to get an exponential function. And there's a way to simplify the exponential function so you don't have this complicated thing up in the power. So basically, I used one of the power rules. Normally, you use it the other way. Normally, if you have things with a like base, when you multiply them, you add the powers. But I basically did it the other way around. Since I'm adding powers, I could multiply them with the like base. So instead of writing e to the 4t plus c, I could separate it and write it as e to the 4t times e to the c. Now, the thing about e to the c is it's just another number. So I've sort of shown this trick before. Since you're doing e to the c, this is just another constant. It's a number to a number. So since we haven't found the constant yet, we can just call that the constant. and it makes that a lot simpler. So I get e to the 4t times c, and it's customary to put that c out in front. So the simplified version of this function would be y equals c times e to the 4t. Now, if you got this, it's not like that's wrong. This is a correct answer, but most people mathematically turn into this because it's easier to work with this. And actually, this should look familiar to you. This is basically akin to that like APERT formula for exponential growth. If you remember the APERT, A equals PER to the T, or E to the RT. So exponential growth and decay looks like this equation, and I like to turn it to this where the constant's out front instead of the constant being up in the power. So if you didn't know to do that, that's why I'm showing it to you. So that end answer would be y equals c e to the 4t. Now, if they gave us an initial condition, we could find that c. They didn't, so it's basically this family of functions, this family of exponential functions solves the initial differential equation. When we do some differential equation applications, this is actually a popular one because this is kind of an easy differential equation. It just says the rate of change is 4 times the original function. What function has that property? This exponential growth function has that property. All right, so those are the solutions. Hopefully you were able to at least get the one on the left and at least part of the one on the right. If not, go over these and make sure you understand them. So this is the last video on just solving the differential equations. Basically, this has most of what you need to know about differential equations, their solutions. We still need to talk about their applications, and slope fields are back because basically these things can lead to you creating slope fields. And the slope fields are a little more complicated than what we did last time, but nothing too crazy. So that's to come in subsequent videos. All right. Until then, enjoy your differential equations and your time off.